What if I told you the universe isn't just a scattered collection of stars and galaxies, but a vast, living network connected by invisible threads that mirror the very structure of the human brain? Picture this: galaxies, billions of them, strung together like beads on a cosmic web, bound by filaments so faint they're nearly impossible to see. These aren't just random pathways, they're the hidden scaffolding of the cosmos, shaping everything from the birth of stars to the fate of entire galaxy clusters. And here's the most mind-bending part. The way these filaments weave through the universe is eerily similar to how neurons connect in our own minds. It's as if the universe itself is thinking, growing, and communicating in ways we're only beginning to understand. This isn't just science fiction. For decades, astronomers have pieced together clues about these mysterious filaments, tracing their faint glow across the darkest stretches of space. They've discovered that these threads aren't empty. They're rivers of superheated gas, dark matter, and unseen forces, pulling galaxies into clusters and guiding their movements over billions of years. But the real breakthrough came when scientists noticed something astonishing. The pattern of these cosmic threads mirrors the neural networks in our brains. The same mathematical rules that govern how neurons fire and connect might also dictate how galaxies align across the universe. It's a connection so profound it blurs the line between the microscopic and the cosmic, suggesting that the universe might operate on principles far more interconnected than we ever imagined. So why does this matter? Because unraveling the secrets of these filaments isn't just about mapping the cosmos, it's about understanding the very blueprint of existence. These invisible threads hold clues to how galaxies form, how dark matter shapes reality, and perhaps even how life itself became possible. Think of it like uncovering the hidden wiring behind everything we see, tracing the lines that link the smallest particles to the largest structures in space. And that's exactly what we're going to explore in this video, a journey deep into the cosmic web, where astronomy meets neuroscience, and where the universe reveals itself not as a chaotic void, but as a finely tuned, astonishingly connected masterpiece. Ready to see the cosmos in a whole new light? Let's begin. To grasp the sheer scale of the cosmic web, let's start with something closer to home: the Internet. Imagine the universe as a global network, where galaxies are cities and these invisible filaments are the fiber optic cables linking them all. But unlike our human-made networks, this cosmic infrastructure wasn't built, it emerged from the very fabric of space-time. In the early universe, tiny fluctuations in density, smaller than a single atom, began to pull matter together. Over billions of years, gravity amplified these faint ripples, sculpting them into vast rivers of dark matter and gas. Today, we see the result: a labyrinth of filaments, some stretching hundreds of millions of light years, with galaxies clustered like glittering nodes at their intersections. The discovery of this structure didn't happen overnight. Astronomers first noticed galaxies weren't scattered randomly, but grouped in strange, thread-like patterns. Then came computer simulations, modeling the universe's evolution from the Big Bang to the present. When scientists fed the laws of physics into these virtual universes, something remarkable happened. The simulations predicted the same intricate web we now observe in the real cosmos. It was a eureka moment. The universe's large-scale structure wasn't just real, it was inevitable, written into the laws of nature from the beginning. But here's where it gets even stranger. These filaments aren't passive threads, they're dynamic, pulsing with energy. Superheated gas, charged particles, and even dark matter flow along them like cosmic currents, funneling material into galaxy clusters. Some filaments act as star factories, compressing gas until it ignites into new suns, while others serve as intergalactic bridges, allowing galaxies to merge and evolve. And just like neural pathways strengthen with use, these cosmic threads grow more defined over time, shaping the universe's destiny. What's truly humbling is how this web connects everything. The same filament guiding a galaxy a billion light-years away might have influenced the Milky Way's birth. It's a reminder that no corner of the cosmos exists in isolation. We're all part of this sprawling, interconnected masterpiece. And as telescopes peer deeper into space, mapping these filaments in ever greater detail, we're not just charting the universe's anatomy, we're decoding the blueprint of existence itself. Dark matter might be invisible, but its influence is written across the cosmos in bold strokes. Imagine trying to build a skyscraper without its steel framework. The visible bricks and glass would collapse under their own weight. That's precisely the role dark matter plays in the universe. Though we can't see it directly, its gravitational pull acts as the invisible skeleton, holding galaxies together and shaping the vast filaments that connect them. Without it, the cosmic web would unravel, leaving galaxies adrift in a formless void. So how do we know dark matter exists if we can't detect it with telescopes? The clues lie in the way galaxies move. Stars on the outer edges of galaxies rotate just as fast as those near the center, defying the laws of gravity as we understand them. The only explanation is that an unseen mass dark matter must be exerting an extra gravitational pull, keeping those stars from flying off into space. Even more compelling is the way galaxy clusters behave. When astronomers observe how these massive structures bend light around them, they're essentially seeing the gravitational fingerprint of dark matter, warping space-time itself. But here's where it gets even more fascinating. Dark matter doesn't just hold galaxies together, it dictates how they're arranged. Computer simulations of the universe show that without dark matter's gravitational influence, galaxies would never have clustered along those intricate filaments we see today. Instead, they'd be scattered randomly like dust in the wind. It's dark matter that drew gas and stars into those cosmic rivers, creating the highways along which galaxies travel and collide. And the strangest part, dark matter might not even be one single thing. Scientists have proposed everything from weakly interacting massive particles to primordial black holes as potential candidates. Some theories even suggest dark matter could interact with itself through unknown forces, adding another layer of complexity to this cosmic mystery. What we do know is that solving this puzzle isn't just about filling a gap in our knowledge, it's about rewriting our understanding of the universe's architecture. The hunt for dark matter is one of science's greatest detective stories. Deep underground, in abandoned mines and beneath mountains, physicists have built ultra-sensitive detectors, hoping to catch a fleeting glimpse of these elusive particles. In space, telescopes map the distortions in light caused by dark matter's gravity, piecing together its hidden structure. Every new discovery brings us closer to answering the fundamental question: what is the universe really made of? One thing's certain: dark matter isn't just a placeholder in our equations. It's the cosmic glue that binds the universe together, the silent architect behind the grand design of the cosmic web. And as we peel back its secrets, we're not just uncovering the hidden mechanics of the cosmos. We're learning how every galaxy, every star, and even our own Milky Way came to be part of this vast, interconnected network. Beneath the dark expanse between galaxies, hidden rivers of scorching gas surge through the cosmic web, carrying the raw materials that birth stars and shape entire galactic neighborhoods. These aren't just empty voids, they're supercharged highways of ionized hydrogen, glowing faintly in X-rays and radio waves, where temperatures soar to millions of degrees. Picture a colossal, invisible pipeline system pumping fuel across the universe, with galaxies tapping into these streams like cosmic service stations. Without them, galaxies would starve, their star-forming factories grinding to a halt. The discovery of these gaseous filaments revolutionized our understanding of how galaxies grow. For years, astronomers puzzled over how distant galaxies, isolated in the vastness of space, kept forming new stars at such astonishing rates. The answer lay in the delicate interplay between gravity and these rivers of gas. As galaxies drift along the cosmic web, they siphon gas from these filaments, drawing it inward like a whirlpool. When enough gas accumulates, it collapses under its own weight, igniting into brilliant clusters of young stars. Some galaxies, like our Milky Way, are frugal with this fuel, forming stars at a steady trickle. Others, especially in the early universe, gorged on these inflows, becoming dazzling starburst galaxies that outshone entire clusters. But the real spectacle begins when these filaments collide. When two streams of gas crash together, the shockwaves can trigger fireworks on a galactic scale. Imagine two fire hoses of superheated plasma crossing paths. The turbulence compresses the gas, igniting frenzied star formation and even feeding supermassive black holes at the hearts of galaxies. In the Virgo cluster, just 55 million light-years away, astronomers have witnessed this firsthand. A galaxy called Messier 87 sits at the crossroads of multiple filaments, its black hole feasting on the incoming gas and shooting out jets of energy visible across the electromagnetic spectrum. Yet these filaments aren't indestructible. When galaxies grow too greedy, they can sever their own lifelines. Supernova explosions and black hole outbursts sometimes blast away the surrounding gas, cutting off the supply and leaving galaxies stranded. It's a cosmic balancing act: too much inflow, and a galaxy burns through its fuel in a blaze of glory; too little, and it fades into a quiet, aging relic. What's truly remarkable is how these gas filaments mirror Earth's own rivers, carving channels through the cosmic landscape and nourishing everything in their path. They remind us that the universe isn't just a collection of isolated objects, but a dynamic, interconnected system where even the emptiest spaces pulse with hidden energy. And as telescopes like the James Webb Space Telescope peer deeper into these gaseous currents, we're not just witnessing the mechanics of star formation, we're tracing the circulatory system of the cosmos itself. Stand at the crossroads of the cosmic web, where galaxies gather like bustling cities at the intersections of invisible highways. These dense clusters, anchored where filaments meet, aren't just random gatherings. They're the universe's synaptic junctions, buzzing with gravitational energy and star-forming activity. The resemblance to our own brain's neural networks is uncanny. Neurons communicate through delicate branches called dendrites, passing electrical signals across tiny gaps called synapses. Now zoom out to the cosmic scale. Galaxies, bound by gravity's pull, exchange gas, stars, and even entire galactic neighborhoods along these filamentary pathways. The structures are so similar that if you superimposed an image of a neuron onto a map of the cosmic web, the lines would align with eerie precision. This isn't mere coincidence, it's a clue to something deeper. Scientists have found that the universe and the brain share startling mathematical similarities. Both systems organize themselves according to the same principles of network efficiency. In your brain, neurons connect in a way that balances energy use with information transfer, creating shortcuts to speed up thought. The cosmic web does the same, with filaments acting as the universe's shortcuts, allowing matter and energy to flow between galaxies with minimal resistance. Even the numbers match. A single cubic millimeter of brain tissue contains around 50,000 neural connections. while a similarly sized slice of the universe holds roughly 50,000 galaxy filaments. The parallels are too precise to ignore. What's even more mind-bending is how both systems evolve. Neurons strengthen their connections through repeated use, a process called synaptic plasticity. The cosmic web exhibits its own version of this. Filaments grow denser and more pronounced as galaxies merge and attract more matter over time. Collisions between galaxy clusters, like the famous bullet cluster, leave behind gravitational scars that reshape the web, much like learning rewires the brain. It's as if the universe is constantly updating its own architecture, adapting to the flow of cosmic traffic. Could this mean the universe is, in some way, thinking? That's a question that straddles the line between science and philosophy. Some theorists propose that these repeating patterns hint at universal laws governing complexity, appearing whether you're studying quantum particles, biological systems, or galactic superclusters. Others caution against drawing direct parallels. After all, galaxies don't process information like neurons do, but the underlying message is clear. From the tiniest synapse to the largest galaxy cluster, nature seems to favor certain blueprints for building interconnected systems. The implications ripple outward. If the universe truly mirrors neural networks, it could reshape how we search for life, design AI, or even interpret the cosmos's ultimate fate. Imagine future telescopes mapping the cosmic web in real time, watching filaments pulse with dark matter like axons firing signals. Or consider simulations where galaxies learn to cluster more efficiently, mirroring machine learning algorithms. This isn't just poetic symmetry, it's a frontier where astrophysics, neuroscience, and computer science might converge to reveal truths about existence itself. For now, the cosmic web remains a silent, shimmering enigma, its filaments whispering secrets across billions of light years. But with every galaxy mapped, every neural network decoded, we inch closer to answering a humbling question. Are we, with our intricate brains, merely echoes of the universe's grand design, or is the universe, in some profound way, echoing us? To unlock the secrets of the cosmic web, scientists have built entire universes inside supercomputers' digital laboratories where they can rewind time to the Big Bang and fast forward through 13.8 billion years of cosmic evolution. These aren't simple animations, they're staggeringly complex simulations that crunch the laws of physics down to equations, calculating how gravity, dark matter, and gas interact on scales from individual galaxies to the entire observable universe. The result, a front-row seat to the birth and growth of the very filaments that bind the cosmos together. Take the Illustris TNG project, one of the most ambitious cosmic simulations ever created. Running on some of the world's most powerful supercomputers, it divides the universe into a grid of over 30 billion cells, each simulating a cube of space roughly 1 million light-years across. As the virtual universe expands, dark matter's invisible tendrils begin to clump under gravity's pull, while rivers of gas flow along these emerging filaments like water-carving channels in sand. Over eons, galaxies spring up at the intersections, mirroring the real universe with uncanny accuracy. What's revolutionary isn't just how well these simulations match telescope observations, it's how they reveal processes we could never witness directly, like the way filaments funnel gas into galaxies, or how black holes at galactic centers can blast away surrounding material, reshaping the web itself. But building these digital universes isn't easy. Even with supercomputers, researchers must make trade-offs. Simulate too large a volume of space, and you lose fine details like individual stars. Focus on a small region with high resolution, and you might miss the broader cosmic context. It's like trying to map every street on Earth while also capturing the entire planet in one photo. To solve this, teams use zoom-in techniques, first modeling the universe at low resolution, then zeroing in on areas of interest, say a single galaxy cluster, with exponentially more detail. These nested simulations have uncovered startling behaviors, like how filaments can stretch and snap during galactic collisions, or how dark matter's ghostly pull can redirect gas flows across millions of light years. The real power of these simulations lies in their predictive ability. Before telescopes like the James Webb or the upcoming Nancy Grace Roman Space Telescope even point at the sky, simulations tell astronomers where to look. When the Euclid Space Telescope recently spotted faint hints of a filament bridging two distant galaxy clusters, it was no accident supercomputers had hinted such structures should exist in that exact region. Simulations also help solve cosmic mysteries like the missing Baryon problem. For decades, astronomers couldn't account for about half the normal matter protons and neutrons the Big Bang should have produced. Simulations pointed to the answer. The matter was hiding in diffuse, million-degree gas strewn along filaments, too faint to detect until cutting-edge X-ray telescopes confirmed it. Yet for all their precision, these digital universes are only as good as the physics we program into them. When simulations and real observations disagree, it's often a sign our understanding of the cosmos is incomplete. For instance, some simulations predict more satellite galaxies around the Milky Way than we've found, hinting that dark matter might behave differently than we thought. Other mismatches suggest gas in filaments could be hotter or more turbulent than models assume. Each discrepancy is a clue pushing scientists to refine their equations and uncover deeper laws governing the cosmic web. What's next? The next generation of simulations will incorporate even wilder physics, like quantum effects in the early universe or the influence of dark energy's mysterious push on filament growth. Meanwhile, machine learning is revolutionizing the field, teaching algorithms to spot subtle patterns in simulation data that humans might miss. Together, these tools are doing more than just mapping the invisible. They're letting us test theories about the universe's fate, from whether filaments will keep weaving new galaxies together, or if dark energy will eventually tear the cosmic web apart. In the end, these supercomputer universes are more than scientific tools, they're time machines, letting us watch the cosmos grow from a primordial soup to the intricate, connected tapestry we see today. And with every simulation, we're not just reconstructing the past, we're writing the playbook for the next era of cosmic discovery. Gravitational lensing is like the universe's own magnifying glass, bending the rules of light to reveal what our eyes could never see. When light from a distant galaxy travels toward Earth, it doesn't always move in a straight line. If it passes near a massive filament or galaxy cluster, the fabric of space-time itself warps, twisting the light's path like a funhouse mirror. The result, a surreal cosmic mirage where galaxies appear stretched into glowing arcs, duplicated like reflections in a kaleidoscope, or even rearranged into ghostly rings. These distortions aren't just artistic quirks of nature, they're precise measurements, allowing astronomers to weigh the invisible threads of the cosmic web by how dramatically they bend the light passing through them. One of the most breathtaking examples lies in the galaxy cluster Abell 1689. From our vantage point, its gravitational grip is so immense that it distorts the light of galaxies far behind it, smearing them into ethereal streaks that curve around the cluster's core like brushstrokes on a canvas. But here's the real magic. By mapping these distortions, scientists uncovered something even more elusive: the faint, sprawling filaments connecting Abell 1689 to neighboring clusters. Like tracing the outline of a shadow, they reconstructed the hidden skeleton of dark matter and gas stretching between galaxies, proving that what looks like empty space is anything but. The math behind gravitational lensing is as elegant as the phenomena themselves. Einstein's theory of general relativity predicted that mass curves space-time, and the more massive the object, the sharper the bend. Filaments, despite their diffuse appearance, contain enough concentrated dark matter to deflect light measurably. By comparing the distorted positions of background galaxies with their expected locations, astronomers create detailed mass maps, essentially X-rays of the cosmic web structure. It's detective work on a galactic scale, where every warped image is a clue to the unseen forces sculpting the universe. Recent advances have taken this technique from theory to transformative tool. The Hubble Space Telescope's Frontier Fields project peered at galaxy clusters with unprecedented depth, capturing lensed galaxies so remote they existed when the universe was a fraction of its current age. Even more groundbreaking, the James Webb Space Telescope now detects lensed light from the first galaxies, their images stretched and amplified by filaments that existed over 13 billion years ago. These cosmic lenses act as natural telescopes, magnifying objects too faint for our instruments to see directly, giving us a free upgrade to observational power, courtesy of space-time itself. But gravitational lensing isn't flawless. Just as ripples on a pond can blur a reflection, the cosmic web's complexity introduces noise. Filaments aren't smooth ropes, they're tangled, knotted with clumps of dark matter and turbulent gas. To untangle the signal, scientists pair lensing data with other techniques like tracking the motion of galaxies within filaments or measuring the X-ray glow of hot gas. Together, these methods paint a multidimensional portrait of the cosmic web, revealing how filaments evolve, how they channel matter, and even how they might have looked during the universe's infancy. What's next? Upcoming observatories like the Vera C. Rubin Observatory will scan the entire sky, capturing millions of lensing events. Machine learning algorithms sift through this avalanche of data, identifying subtle distortions missed by the human eye. With each new map, we're not just filling in blanks, we're rewriting the atlas of the cosmos, proving that even the darkest corners of space are etched with the fingerprints of gravity. And as these invisible threads come into focus, they remind us that the universe's greatest secrets aren't always hidden in the light. Sometimes they're written in the bends. The sheer scale of cosmic filaments defies human comprehension. They're not just large, they're unfathomably vast. Imagine a single thread stretching from one end of the observable universe to the other, weaving through galaxies like an invisible backbone. The Hercules Corona Borealis Great Wall, a filament complex so enormous it dwarfs everything else we've discovered, spans an astonishing 10 billion light-years. That's nearly a tenth of the diameter of the entire observable universe. To put that in perspective, if our Milky Way were the size of a grain of sand, this structure would stretch from New York to Sydney. It's not just a cosmic curiosity, it's a boundary-pushing enigma that forces us to rethink the very limits of what's possible in our universe. How do these filaments grow to such mind-bending proportions? The secret lies in the universe's infancy. In the first moments after the Big Bang, quantum fluctuations, tiny ripples in the fabric of space-time, imprinted faint variations in density across the cosmos. Over billions of years, gravity amplified these ripples, pulling matter into the denser regions while leaving voids between them. The result? A sprawling network where filaments form the borders between these cosmic bubbles, growing longer and more defined as the universe expands. But here's the twist. According to our current understanding of cosmology, structures this massive shouldn't exist. The Hercules Corona Borealis Great Wall, for example, challenges the cosmological principle, the idea that the universe should look roughly the same no matter where you observe it from. Finding something so colossal suggests the universe might be far lumpier and more irregular than we ever anticipated. Mapping these titanic filaments is like trying to trace the outline of a continent while standing on one of its beaches. Astronomers use galaxy surveys, massive 3D maps plotting the positions of millions of galaxies, to reconstruct the filaments' paths. Projects like the Sloan Digital Sky Survey have revealed intricate webs where galaxies cluster along these threads like pearls on a string. But the real breakthroughs come when we combine these maps with gravitational lensing and X-ray observations, revealing the invisible dark matter and superheated gas that make up the filament's true mass. In the case of the Pisces Cetus supercluster complex, another filament spanning over 1 billion light-years, scientists found it contains enough mass to influence the motion of thousands of galaxies, tugging them along like leaves caught in a river's current. What's truly humbling is how these structures redefine our place in the cosmos. Our Milky Way resides in a relatively quiet suburban neighborhood of the Laniakea supercluster, itself just one branch of an even larger filament. But even Laniakea, which spans 500 million light-years, is a mere speck compared to the Hercules Corona Borealis Great Wall. These discoveries force us to confront an unsettling truth. We might be living in a universe where the largest structures are so immense, they stretch beyond the limits of what we can observe. Some theorists speculate that filaments could even connect multiple universes in a vast multiverse, though that remains firmly in the realm of hypothesis. The more we study these colossal formations, the more questions they raise. Do filaments have an upper size limit, or could there be even larger structures lurking just beyond our observational horizon? How do they influence the universe's expansion, and could their gravitational pull be shaping the fate of everything we see? Each answer peels back another layer of cosmic mystery, reminding us that the universe's grandest designs are still waiting to be uncovered. And as telescopes grow more powerful, we're not just charting these giants, we're learning to see the universe as it truly is, an interconnected tapestry where the threads are longer, stranger, and more magnificent than we ever dreamed. Galaxies aren't solitary islands drifting through the void, they're products of their environment, shaped by the invisible currents of the cosmic web. Think of filaments as galactic highways, where the traffic of gas, stars, and dark matter dictates a galaxy's destiny. Those lucky enough to reside along these bustling corridors thrive, feasting on a steady supply of raw material to fuel star birth and black hole growth. Meanwhile, galaxies stranded in the quiet backwaters between filaments face a lonelier fate, their star-forming factories sputtering out as their gas reserves dwindle. This isn't just cosmic chance, it's a fundamental rule of galactic evolution, written into the fabric of the universe itself. Take the Milky Way's own history as an example. Our galaxy sits within a filament of the Laniakea supercluster, a position that's allowed it to grow steadily over billions of years. By siphoning gas from this cosmic tributary, the Milky Way has maintained a balanced diet of star formation, not too frantic, not too stagnant, resulting in the vibrant spiral we see today. But contrast that with galaxies like Messier 87, the colossal elliptical at the heart of the Virgo cluster. Perched at a crowded filament intersection, it's undergone multiple galactic mergers, its supermassive black hole gorging on incoming gas and launching jets that heat the surrounding web. These two galaxies couldn't be more different, yet their divergence stems largely from their positions in the cosmic network. The real drama unfolds when galaxies collide. Filaments don't just nourish galaxies, they orchestrate their mergers. As galaxies flow along these gravitational channels, they're funneled toward dense nodes where clusters form, increasing the odds of violent encounters. When two gas-rich galaxies merge, the shockwaves compress their fuel, triggering starbursts so intense they can outshine an entire galaxy. But there's a catch: these fireworks come at a cost. The same collision can funnel gas into the central black hole, awakening it as a quasar whose fierce winds blast away the remaining star-forming material. It's a cosmic catch-22. The very process that creates a galaxy's brightest era also hastens its decline into a quiet, aging elliptical. Yet not all filament dwellers face the same fate. Recent observations reveal a startling twist. Some galaxies manage to avoid this fiery climax. In less crowded filaments where traffic is lighter, galaxies can merge gently, preserving their gas and spiral structure. Others, like the Andromeda Galaxy, show signs of past collisions without the telltale scars of violent quasar activity. The difference: their mergers happened along quieter stretches of the cosmic web, where gas flows were steadier and black holes remained relatively calm. It's a reminder that filaments aren't uniform. Their density, geometry, and even the angle at which galaxies approach them can alter a galaxy's life story. The most striking evidence of this cosmic influence comes from the universe's adolescence. In the early cosmos, filaments were narrower and more abundant, creating a frenetic environment where galaxies grew up fast. Telescopes like the James Webb have spotted young galaxies along these ancient threads. Their star formation rates 100 times higher than the Milky Way's today. But without the stabilizing influence of mature filaments, many burn through their gas too quickly, ending their star-forming days prematurely. Only those anchored to the evolving web's strongest filaments survive to become the grand galaxies we see now. What does this mean for the future? As the universe expands and dark energy stretches the cosmic web, filaments will grow sparser, leaving galaxies increasingly isolated. Star formation will slow, mergers will become rare, and the universe will drift toward a quieter, darker era. But for now, we're living in the golden age of galactic evolution, where the invisible threads of the cosmic web still hum with activity, weaving the destinies of galaxies in ways we're only beginning to decode. The resemblance between the cosmic web and the human brain goes far deeper than their striking visual similarity. It's etched into the very mathematics that govern them. At first glance, comparing neurons to galactic filaments might seem like poetic metaphor, but zoom in closer, and you'll find both systems obey the same unspoken rule: efficiency. Neurons in your brain aren't randomly connected. They form precise pathways that minimize signal delay, ensuring thoughts fire at lightning speed. Cosmic filaments operate on an eerily parallel principle. They're the universe's solution to minimizing gravitational energy, the most efficient routes for matter to flow across unimaginable distances. It's as if nature, whether working on the scale of synapses or superclusters, keeps rediscovering the same blueprint. To understand why this matters, let's hear from Dr. Sarah Walker, a computational neuroscientist at MIT. When we map neural networks, she explains, we see branching patterns that balance connectivity with resource conservation. Too many direct links would overload the system, too few would slow communication. The brain finds a sweet spot, and shockingly, so does the cosmos. Her team analyzed cosmic filament maps alongside brain scans, discovering both share a property called small world architecture. This means most connections are local, but critical long-range shortcuts exist, allowing rapid communication whether between distant neurons or far-flung galaxies. Meanwhile, astrophysicist Dr. Carlos Hernandez at Caltech studies how dark matter sculpts these cosmic pathways. Gravity is the universe's ultimate efficiency expert, he notes. Filaments emerge where matter can flow with the least resistance, just like water finding the downhill path. His simulations reveal that when two galaxy clusters merge, their connecting filament reconfigures to preserve this gravitational economy, much like neural pathways rewire after learning a new skill. The similarities even extend to growth patterns. Neurons strengthen frequently used connections by adding synapses, while filaments thicken as galaxies funnel more matter into them. But here's where the parallels get provocative. Some theorists argue these aren't just analogies, they are evidence of universal network laws. Physicist Dr. Leila Chen, who specializes in complex systems, points to slime molds as another example. When placed in a maze with food sources, these single-celled organisms grow tendrils that perfectly mirror Tokyo's subway system or the cosmic web. No brain, no gravity, just a blind drive toward optimal connectivity. Her research suggests that any system, whether biological, cosmic, or even man-made like the internet, tends toward similar structures when balancing cost and efficiency. Could this mean we've stumbled upon a fundamental truth about how complexity emerges? The answer remains tantalizingly uncertain. Critics caution that while the math aligns, the underlying mechanisms differ radically. Neurons communicate via electrochemical pulses, while filaments are shaped by gravity's relentless pull. Yet even skeptics admit the consistency is startling. As telescope resolutions sharpen and brain mapping advances, we're finding more overlaps, like how both neural networks and cosmic filaments exhibit fractal-like self-similarity, repeating their patterns at different scales. Perhaps the most profound implication lies in how we study the universe itself. Neuroscientists are borrowing algorithms from cosmology to model brain connectivity, while astronomers apply neural network theory to predict filament growth. It's a rare moment where two seemingly unrelated fields illuminate each other, hinting that the universe's greatest mysteries might not be locked within individual disciplines, but in the hidden connections between them. Whether this is coincidence or cosmic inevitability, one thing's clear: the next breakthrough in understanding our minds or our universe might just come from staring at the other. To grasp how the cosmic web's filaments first took shape, we need to rewind time, all the way back to the universe's first fleeting moments. In the searing heat of the Big Bang, space wasn't smooth and uniform. Instead, it crackled with quantum fluctuations, microscopic ripples in energy so tiny they'd vanish in a trillionth of a second under normal circumstances. But this wasn't a normal environment. The infant universe was undergoing something extraordinary: inflation, a period of exponential expansion where space itself stretched faster than light. In less than the blink of an eye, those quantum ripples were blown up to cosmic proportions, frozen into the fabric of spacetime like footprints in rapidly hardening concrete. These stretched fluctuations became the universe's first uneven patches, slightly denser regions where matter would later gather, and thinner zones that would evolve into vast cosmic voids. Picture a balloon inflating with tiny wrinkles on its surface. As the balloon grows, those wrinkles expand into sprawling ridges and valleys. That's essentially what happened to space, except instead of a rubber surface, these wrinkles became the gravitational wells that would eventually pull galaxies together. The denser regions acted like cosmic glue, attracting dark matter and gas, while the emptier areas stretched further apart, creating the vast filament-lined voids we see today. Here's where it gets even more fascinating. The pattern of these fluctuations wasn't completely random. It followed a precise mathematical signature known as the Harrison-Zeldovich spectrum. This cosmic fingerprint predicted exactly how matter should clump at different scales, from the tiniest galaxy clusters to the largest superclusters. Decades later, when astronomers mapped the cosmic microwave background, the afterglow of the Big Bang, they found that same fingerprint imprinted in the temperature variations of the early universe. It was like uncovering the architect's original sketch, proving that the seeds of today's cosmic web were planted in those first chaotic moments. But how did these subtle ripples grow into the universe's connective tissue? Gravity played the long game. Over hundreds of millions of years, dark matter, the universe's invisible scaffolding, began collapsing into the denser regions, forming a network of delicate strands. Gas followed, streaming along these dark matter highways, cooling and condensing into galaxies at the intersections. Simulations show this process unfolding like a slow-motion cosmic ballet, with filaments emerging as the natural pathways where matter flows most efficiently. The initial quantum randomness didn't just dictate where filaments formed, it also influenced their thickness, their curvature, even the angles at which they intersect. What's truly humbling is realizing that the Milky Way, Earth, and even our own existence trace back to these quantum ripples. Had the fluctuations been slightly stronger, filaments might have condensed too quickly, creating a universe of overcrowded galaxy clusters with no room for stable solar systems. Slightly weaker, and matter might never have clumped enough to ignite the first stars. Instead, we live in a Goldilocks cosmos where quantum randomness conspired with gravity to weave a web just structured enough to build galaxies, yet sparse enough to let them breathe. This isn't just a story about the past, it's a key to the future. By studying these primordial fluctuations, scientists can predict how filaments will evolve billions of years from now, whether dark energy will eventually tear them apart, or if new threads will continue to form. Every time we map a filament or simulate the early universe, we're decoding a message from the dawn of time, written in the language of quantum mechanics and etched across the sky. For decades, astronomers faced a cosmic accounting problem that refused to add up. When they tallied all the ordinary matter, the protons and neutrons that make up stars, planets, and everything we can see, they came up startlingly short. According to the Big Bang's playbook, the universe should contain about twice as much of this baryonic matter as we've been able to locate. The missing half became one of cosmology's most persistent mysteries, hiding in plain sight while eluding every telescope pointed at the sky. But the answer, it turns out, was woven into the very fabric of the cosmic web, all along, lurking in the faint, diffuse gas strewn between galaxies along those invisible filaments. The search for these missing baryons reads like a detective story spanning generations of scientists. Early clues came from studying the cosmic microwave background, the afterglow of the Big Bang. Its subtle temperature variations revealed how much ordinary matter the universe began with. Yet when astronomers counted up all the visible stars, galaxies, and gas clouds, they found barely half the expected amount. Where could the rest be hiding? Some theorized it might be tied up in exotic objects like rogue planets or failed stars, but these couldn't account for the staggering deficit. Others suggested it had been blown out of galaxies by supernova winds, lost in the voids between cosmic structures. The breakthrough came when researchers realized the answer wasn't in discrete objects at all. It was in the nearly invisible plasma threading the cosmic web. Detecting this elusive gas required entirely new observational techniques. Unlike the dense clouds in galaxies, filament gas is so hot, millions of degrees, that it doesn't emit visible light. Instead, it glows faintly in X-rays and warms the cosmic microwave background in predictable ways. Telescopes like the European Space Agency's XMM Newton and NASA Chandra began picking up these signals, revealing vast reservoirs of ionized hydrogen and helium stretched along filaments. Even more telling were distortions in the light from distant quasars, which showed absorption lines where the gas had stripped electrons from passing photons. Piece by piece, the evidence mounted. The missing baryons weren't lost, they'd been hiding in plain sight, woven into the universe's largest structures. One of the most dramatic confirmations came from the E-Rosetta X-ray telescope, which mapped the hot gas in a filament connecting two galaxy clusters 400 million light-years away. The data showed a bridge of superheated plasma stretching over 50 million light-years, containing more mass than all the stars in the clusters combined. Similar observations now suggest that up to 90% of the universe's ordinary matter resides in these filamentary reservoirs, enough to finally balance the cosmic books. But the hunt isn't over. The remaining baryons are thought to be even more diffuse, spread across intergalactic space in a mist so thin it defies current detection. Solving this puzzle does more than just complete our inventory of cosmic matter. It reshapes how we understand the universe's evolution. These hidden gas reservoirs act as both fuel depots and recycling centers, channeling material into galaxies while absorbing the heavy elements blown out by supernova. They're the reason galaxies can keep forming stars billions of years after their initial gas supply should have been exhausted, and they may hold clues to one of the universe's greatest unsolved mysteries: why the expansion of space is accelerating. Some theories propose that dark energy's push could be heating this gas, altering how filaments distribute matter across cosmic time. As next-generation telescopes like the Athena X-ray Observatory come online, we're poised to map these baryonic rivers in unprecedented detail, tracing how they've shaped galaxies from the universe's first epochs to the present day. What began as a discrepancy in a physicist's notebook has revealed one of the cosmos' best-kept secrets: that the emptiness between galaxies isn't empty at all. It's a dynamic, ever-changing network of matter, pulsing with energy and possibility, waiting to tell its story. Hidden within the delicate strands of the cosmic web, an invisible force weaves through the superheated gas and dark matter: magnetic fields. These intergalactic power lines, millions of times weaker than Earth's own magnetic field, yet spanning hundreds of millions of light-years, are the universe's silent architects. Unlike the chaotic magnetism of stars or galaxies, filament fields are impossibly ordered, their lines stretching along the filament's lengths like cosmic harp strings. They don't just coexist with the cosmic web. They shape it, stabilizing rivers of gas against turbulence and guiding the flow of matter with an unseen hand. The discovery of these fields reads like a triumph of cosmic forensics. Since magnetism emits no light of its own, astronomers had to become detectives, searching for its fingerprints in the polarized glow of distant quasars. As light from these brilliant objects passes through filaments, the magnetic fields twist its polarization, the orientation of its light waves like a subtle cosmic prism. Instruments like the Atacama Large Millimeter Array in Chile have captured this telltale twist, revealing fields strong enough to sculpt gas flows but too weak to tear galaxies apart. It's a delicate balance, one that suggests these fields didn't arise by chance but were woven into the universe's fabric from the beginning. What's truly astonishing is how these fields defy expectations. In most of space, magnetism is messy. Think of the tangled fields around black holes or the twisted loops on the sun's surface. Filament fields, by contrast, are eerily uniform, their lines running parallel for distances that would take light eons to cross. Simulations suggest this order stems from the filament's birth. As gas flowed along dark matter's gravitational scaffolding in the early universe, it stretched primordial magnetic fields like taffy, aligning them into vast cosmic currents. Over billions of years, these fields grew stronger, acting as cosmic rail tracks that kept gas from spilling into the voids. But magnetism's role goes beyond mere structure. These fields are particle accelerators on a galactic scale. When charged particles, protons, electrons, even cosmic rays enter a filament, the magnetic fields whip them to near light speeds. Some particles spiral along field lines, emitting faint radio waves that telescopes like the Low-Frequency Array in the Netherlands have begun to detect. Others might escape entirely, seeding intergalactic space with high-energy radiation. There's even evidence that filament fields can redirect jets from supermassive black holes, bending these beams of plasma into unexpected shapes like a prism bending light. The biggest mystery where these fields originated. One theory points to the universe's infancy, when violent phase transitions in the primordial plasma could have generated magnetism on cosmic scales. Another suggests the accumulated fallout from countless supernovae, their magnetic debris swept into filaments over eons. The most tantalizing idea ties them to dark matter itself, that this elusive substance might interact with magnetic fields in ways we've yet to imagine. As we map these invisible forces, we're not just solving a cosmic puzzle, we're uncovering a new layer of the universe's interconnectedness. From guiding galaxy formation to accelerating particles across intergalactic space, these subtle fields prove that even the emptiest corners of the cosmos hum with unseen energy. And with every new observation, we're learning that the cosmic web isn't just held together by gravity, it's stitched with magnetic threads, quietly orchestrating the universe's grand design. Between the glowing threads of the cosmic web lie the universe's most desolate frontiers, vast, yawning voids where galaxies are so scarce you could travel 100 million light-years without seeing a single star. These aren't just empty pockets, they're colossal bubbles of near-nothingness, some so large they defy conventional physics. Take the Boötes Void, a spherical abyss spanning 330 million light-years. If our Milky Way sat at its center, we wouldn't have discovered other galaxies until the 1960s. That's how profoundly empty this region is. Yet these voids aren't cosmic mistakes. They're critical players in shaping the universe's architecture, their emptiness sculpting the filaments around them like invisible hands pressing into wet clay. Why do such extreme voids exist? The answer lies in the universe's earliest moments. During inflation, quantum fluctuations created slight overdensities where filaments would later form, but between them, regions emerged with significantly less matter. As the cosmos expanded, gravity amplified this imbalance. Matter flowed toward the denser filaments, leaving the underdense regions to stretch and empty further. Picture a balloon with weak spots when inflated. Those thin areas grow disproportionately, becoming vast stretches of taut emptiness. Today, voids make up over 80% of the universe's volume, yet contain less than 10% of its galaxies. Their gravitational influence, however, is anything but negligible. Voids actually push the cosmic web into sharper relief. Without their repulsive effect, yes, repulsive filaments might have dissolved into a homogeneous cosmic soup. Here's how it works. While gravity pulls matter into filaments, the expanding voids create a counterforce, essentially shoving galaxies toward the web's intersections. This cosmic tug-of-war results in filaments that are thinner and more defined at their edges facing voids, almost like tree roots growing around rocks. The effect is so pronounced that some filaments appear slightly curved where they skirt particularly large voids, their shapes molded by absence as much as presence. But voids aren't completely empty. Scattered, void galaxies drift through these deserts like lone ships in an ocean, often smaller and bluer than their filament-dwelling cousins. Isolated from galactic crowds, these misfits evolve differently. With fewer collisions, they retain more gas, forming stars at a steadier pace. Some even harbor supermassive black holes that seem oddly massive for their host galaxies, suggesting voids might preserve ancient cosmic relics that filaments have long since disrupted. Then there's the mysterious void gas, faint wisps of hydrogen so diffuse they emit no light, only detectable when their shadows block distant quasars. This gas might hold clues to another puzzle: why voids appear to be expanding faster than the rest of the universe. That accelerated expansion is where voids become cosmic laboratories. Dark energy, the enigmatic force driving the universe's expansion, seems to exert extra influence in these empty regions. With so little matter to resist it, dark energy stretches voids more aggressively, causing their walls to thin and their volumes to grow. Astronomers now use voids as natural dark energy detectors, measuring how their shapes distort over billions of years. The upcoming Vera C. Rubin Observatory will map millions of voids, testing whether dark energy's strength changes over time, a discovery that could rewrite our understanding of the universe's fate. Perhaps the most humbling realization is that we're floating in a void's outskirts right now. Our local void, a 500 million light-year gap, nudges the Milky Way and neighboring galaxies toward the Laniakea supercluster's bustling filament network. It's a reminder that even as we marvel at the cosmic web's glowing threads, the true architects of large-scale structure might be these immense, silent nothings shaping the universe not by what they contain, but by everything they don't. The next decade of astronomy promises to rewrite our understanding of the cosmic web, with groundbreaking telescopes poised to peel back layers of the universe we've never seen before. At the forefront is the James Webb Space Telescope, already revealing filaments in the early universe with staggering clarity. But Webb is just the beginning soon. Instruments like the Square Kilometre Array will map hydrogen gas along filaments across billions of light years, while the Nancy Grace Roman Space Telescope's wide-field surveys will stitch together the Webb's full architecture like never before. These aren't just incremental upgrades, they're quantum leaps in observational power, capable of spotting filaments 10 times fainter than current technology allows. What makes these next-gen tools so revolutionary? It's all about sensitivity and scope. The Square Kilometre Array, with its thousands of radio antennas spanning 2 continents, will detect the faint whisper of neutral hydrogen atoms drifting along filaments, a feat equivalent to hearing a single raindrop in a thunderstorm from halfway across the globe. This hydrogen acts as a cosmic tracer, illuminating filaments too diffuse for optical telescopes to spot. Meanwhile, the European Space Agency's Euclid mission is combining visible and infrared light to construct a 3D map of dark matter's distribution along the web, revealing how its invisible gravity wells sculpt gas flows across 11 billion years of cosmic history. But the real game-changer lies in how these instruments work together. Webb's infrared eyes penetrate dust clouds to study star formation within filament-fed galaxies, while the upcoming Athena X-ray Observatory measures the million-degree gas between them. Cross-referencing these datasets will let scientists track matter's journey from intergalactic currents to newborn stars, a cosmic supply chain we've only glimpsed in fragments. Early tests hint at surprises, like preliminary Webb data suggesting some filaments in the early universe were denser than models predicted, potentially rewriting how quickly the cosmic web matured after the Big Bang. Perhaps most exciting are the unknown phenomena these telescopes might uncover. Could there be ultra-dark filaments dominated entirely by exotic particles? Might we find cold flows, pristine rivers of gas untouched by star formation? That theory predicts, but none have conclusively observed. And what about the possibility of magnetic fields spanning entire superclusters, detectable through their polarization of ancient light? The answers could reshape fundamental physics, offering clues about dark matter's nature or whether additional forces sculpt the web beyond gravity. This observational renaissance comes just in time. As dark energy accelerates the universe's expansion, filaments are stretching thinner, their gas cooling and dissipating. Within 100 billion years, the cosmic web may fade beyond recognition, making this our last cosmic epoch to witness its structure in full glory. The data pouring in from these telescopes won't just fill textbooks, it'll preserve a snapshot of the universe in its prime, a legacy for civilizations far in the future who'll peer into a far emptier cosmos. For now, we stand at the threshold of discovery, instruments poised to decode the universe's grand design as never before. At the heart of nearly every galaxy, a cosmic predator lies in wait, a supermassive black hole, millions to billions of times heavier than our Sun. These gravitational monsters don't just sit idle, they feast on the universe's bounty, growing larger and more powerful over eons, but their meals don't arrive by chance. The cosmic web's filaments act like celestial conveyor belts, channeling gas, dust, and even entire stars directly into their maws. This isn't just a passive delivery system, it's an intricate gravitational dance where filaments don't merely feed black holes, they regulate their fury, shaping the destiny of entire galaxies in the process. Picture a black hole as a whirlpool at the center of a galactic river. The filament is the river itself, carrying a steady flow of material from the intergalactic hinterlands toward the galaxy's core. As this gas spirals inward, it heats up to millions of degrees, glowing brilliantly in X-rays before vanishing beyond the event horizon. But here's where things get fascinating. Not everything makes it into the abyss. Some gas gets caught in magnetic fields or whipped up by the black hole's rotation, creating colossal jets of plasma that shoot out at nearly light speed. These jets can stretch for thousands of light years, punching through the galaxy and beyond, sometimes even reheating the very filaments that fed the black hole in the first place. This creates a cosmic feedback loop of staggering scale. When filaments deliver too much gas too quickly, the black hole enters a frenzy, its jets blasting outward with enough energy to push surrounding gas away. This temporarily starves the black hole while also preventing nearby gas from cooling enough to form new stars. It's like a thermostat for galactic evolution: too much activity, and the system shuts down. Conversely, when filaments provide a steadier, more measured flow, the black hole's output remains moderate, allowing star formation to continue across the galaxy. Observations of galaxy clusters like Perseus reveal this balance in action, where cavities carved by black hole jets are surrounded by regions of intense star birth, all orchestrated by the filament's delicate gas supply. Some of the most dramatic examples occur in brightest cluster galaxies, which sit at the crossroads of multiple filaments. Take the Phoenix Cluster's central galaxy, where astronomers witnessed a black hole feasting on filament-fed gas while simultaneously birthing more stars per year than our entire Milky Way. The filaments here act like a cosmic throttle, delivering just enough fuel to power the black hole's jets, which then compress surrounding gas into new stars rather than blowing it away. It's a rare equilibrium that challenges our understanding of how these systems interact, proving filaments don't just passively connect galaxies, they actively mediate their growth. Yet black holes aren't always obedient to their filamentary masters. Occasionally, they rebel. In galaxy NGC 5548, a supermassive black hole's outburst created a wind so powerful it blocked 90% of the incoming filament gas, effectively putting itself on a starvation diet. Similar events have been spotted in other galaxies, suggesting black holes can temporarily override the cosmic web's influence, though never permanently. Given enough time, gravity always wins. Filaments resume their flow, and the cycle begins anew. The implications ripple across cosmic time. In the early universe, filaments were denser and more plentiful, meaning black holes had all-you-can-eat buffets that allowed them to grow to staggering sizes quickly. Today, as filaments thin and dark energy stretches the cosmic web, black hole meals are becoming scarcer, their outbursts less frequent. This slow cosmic dimming hints at a future where filaments may no longer sustain them, leaving galaxies to evolve in silence. But for now, we're witnessing the golden age of this gravitational symbiosis where invisible threads weave together the fates of black holes, galaxies, and the universe itself. Could our universe's intricate web of filaments be just one variation in an infinite cosmic tapestry? The multiverse hypothesis, the idea that our universe might be one of many, raises a profound question. If other universes exist, would they too be threaded with these same gossamer strands of matter and dark energy? Some physicists argue that filaments aren't just a quirk of our particular cosmos, but a universal inevitability, emerging from fundamental laws that would govern any space-time. Others counter that without an identical cosmic recipe, the precise mix of dark matter, inflation, and quantum fluctuations that shaped our web, alternative universes might look utterly alien. Take cosmic inflation theory, which suggests our universe ballooned from a quantum speck during the Big Bang. In most versions of this model, the same quantum processes that seeded our filaments would play out in any sibling universe, though the resulting web might vary in density or scale. Simulations of bubble universes, hypothetical regions where inflation ended at different times, show many develop similar large-scale structures, with matter clustering along interconnected threads. Even in universes with stronger gravity or faster expansion, computer models reveal filaments forming, though some appear sparser or more tangled than ours. This hints that the cosmic web might be as fundamental to spacetime as mountains are to planetary geology, not identical everywhere, but arising from universal principles. Yet there are wild cards that could rewrite the rules entirely. In a universe where dark energy dominates earlier or dark matter behaves differently, filaments might never fully coalesce, leaving matter scattered like sand in wind. Some string theory models propose universes with extraspatial dimensions, where gravity's altered strength could prevent filament formation altogether. Then there's the most radical idea that certain universes might lack dark matter entirely, relying solely on visible matter's weak gravity. In those realms, galaxies could form in isolation, drifting like lonely ships without the connective tissue we take for granted. The real test may lie in the math. When physicists analyze the equations governing structure formation, they find a surprising robustness. Filaments emerge across a wide range of initial conditions, like how snowflakes always form intricate patterns despite varying temperatures. This mathematical resilience suggests that while other universes' webs might differ in detail, the underlying architecture could share deep similarities. It's akin to how trees worldwide branch in fractal patterns despite growing in diverse environments, a hint that some organizational principles transcend local physics. Of course, without observational evidence from other universes, this remains speculative, but here's a tantalizing thought. If the multiverse exists and filaments are universal, then our cosmic web might not just connect galaxies, it could be linking us to realities beyond our own, threads in a tapestry vaster than we dare imagine. Until science finds a way to peer across the cosmic veil, the question lingers: is our universe's structure a happy accident, or an inevitable verse in a grand, repeating cosmic poem? The cosmic web we see today wasn't always this intricate tapestry of filaments. It's a structure that's been evolving since the first sparks of the universe. Rewind 13 billion years and you'd find a far simpler scene: faint tendrils of dark matter and gas, barely denser than their surroundings, stretching across a hot, opaque cosmos. These primordial threads were the universe's first connective tissue, emerging from the faint gravitational fingerprints left by quantum fluctuations in the Big Bang's aftermath. In those early epochs, filaments were like delicate spiderwebs, easily torn apart by the violent bursts of energy from newborn stars and black holes. Yet over time, gravity's relentless pull transformed them into the robust highways we observe today, thick with galaxies and glowing gas. Simulations let us watch this cosmic metamorphosis unfold in fast forward. In the universe's youth, filaments were narrow and chaotic, crisscrossing in a frenzied network that resembled a tangle of roots. Galaxies along these threads were few and far between, often solitary and gas-rich, burning through their fuel in brilliant but short-lived starbursts. As eons passed, gravity worked its magic. Filaments grew denser, drawing in more matter and merging with neighboring strands like rivers converging into a delta. The galaxies within them began to cluster at intersections, forming the glittering nodes we now recognize as galaxy clusters. Meanwhile, the voids between filaments expanded, their emptiness pushing matter into ever sharper relief, like ink pooling at the edges of a watercolor painting. But the cosmic web story doesn't end there. Peer into the far future and dark energy, the mysterious force accelerating the universe's expansion, steals the spotlight. As space stretches faster, filaments face a cosmic tug of war. Gravity tries to hold them together, while dark energy pulls them apart, thinning the threads until they resemble fraying ropes. Galaxies along these fading filaments will find themselves increasingly isolated, their fuel lines cut off as the gas between them grows too diffuse to traverse. Star formation will sputter out, and black holes will go dormant, leaving the universe darker and quieter with each passing billion years. Simulations predict that in about 100 billion years, the cosmic web may be so stretched that observers, if any remain, would struggle to recognize its structure at all. What's fascinating is how this evolution mirrors life cycles we see on Earth. Filaments grow like forests, starting as sparse saplings before maturing into dense canopies, only to eventually decay. Their mergers resemble continental collisions, reshaping the cosmic landscape in slow motion. Even their eventual dissolution echoes the way Earth's mountains erode over geological time, inevitable, gradual, and governed by forces beyond their control. Yet, unlike forests or mountains, the cosmic web's timescales are so vast that human history is less than a blink in comparison, the most humbling realization. We're witnessing the cosmic web in its prime, this very moment as telescopes map filaments with unprecedented detail, captures a fleeting golden age after the chaos of the early universe but before the long fade into darkness. It's a reminder that the universe isn't just a static backdrop but a dynamic, ever-changing stage, with filaments as its evolving script. And as we piece together their past and predict their future, we're not just studying the universe's anatomy, we're reading its autobiography, written in gravity, dark matter, and time. Galaxies aren't stationary islands in space, they're travelers on an epic journey, drifting along the cosmic web's filaments like ancient civilizations following rivers through uncharted lands. These intergalactic superhighways don't just connect points in space, they dictate the motion of entire galactic neighborhoods, including our own Milky Way. Picture a celestial conveyor belt where gravity's pull guides galaxies toward dense intersections, much like tributaries merging into a mighty river. Right now, the Milky Way is riding one of these filaments, hurtling toward the Virgo cluster at over 600,000 miles per hour. But our ultimate destination lies even farther, the mysterious Great Attractor, a gravitational anomaly so powerful it's pulling thousands of galaxies toward it like a cosmic whirlpool. The Milky Way's migration story is written in the stars literally, by mapping the motions of nearby galaxies and tracing their trajectories backward. Astronomers have reconstructed our galactic neighborhood's history. We're part of the Laniakea supercluster, a sprawling network of 100,000 galaxies all flowing toward the same gravitational focal point. This motion isn't random. It follows the contours of filaments like the Pisces Cetus complex, a thread of dark matter and gas stretching over 1 billion light-years. Along this highway, galaxies jostle like commuters in cosmic traffic, some merging in spectacular collisions, others slipping past one another in a delicate gravitational dance. Our closest neighbor, Andromeda, is also riding this current, destined to collide with the Milky Way in about 4 billion years, a fate orchestrated by the filament we both share. But what propels galaxies along these routes? It's a combination of push and pull. Behind us, the expansive local void exerts a subtle repulsive force, nudging galaxies toward denser regions, while ahead, the gravitational tug of the Great Attractor acts like a cosmic siren song. These forces work in tandem with the filament's own gravity, which channels galaxies along its length like a groove guiding a marble. Even stranger, galaxies don't move in straight lines, they follow the filament's curves, spiraling toward nodes where multiple threads converge. This explains why galaxy clusters often appear to spin, a phenomenon once thought impossible on such vast scales. The Great Attractor itself remains one of the cosmos' most intriguing puzzles. Hidden behind the Milky Way's dusty central bulge, this region of space centered near the Norma cluster holds the mass equivalent of tens of thousands of galaxies. Yet visible matter accounts for only a fraction of its pull, suggesting dark matter's invisible hand is at work. Some theories propose it's not a single object but a confluence of multiple superclusters, their combined gravity creating a focal point for our filament's flow. Whatever its nature, its influence is undeniable. Everything in our corner of the universe, from the tiniest dwarf galaxy to the mightiest clusters, is caught in its current. Looking ahead, the Milky Way's journey will only grow more dramatic. As we approach the Great Attractor, our filament will merge with others, funneling us into an ever denser cosmic metropolis. Billions of years from now, the Milky Way may find itself at the heart of a gargantuan galaxy cluster, surrounded by remnants of ancient collisions. Yet even this isn't the end of the road. Beyond the Great Attractor lies an even larger gravitational anomaly, the Shapley supercluster, a staggering collection of matter pulling us deeper into the cosmic web's embrace. This grand migration isn't unique to our galaxy. Across the universe, filaments shepherd galaxies toward their fates, shaping the universe's large-scale structure, one gravitational nudge at a time. By studying these pathways, we're not just mapping our own trajectory, we're unraveling the story of how all galaxies move, collide, and evolve in this vast, interconnected cosmos. And as we peer deeper into the web's architecture, we're reminded that the night sky isn't a static painting. It's a snapshot of an ever-shifting masterpiece, with every galaxy playing its part in the dance. Deep in the fabric of the cosmos, an invisible battle rages, one that will determine the fate of everything we see. On one side, the cosmic web's filaments, those vast rivers of dark matter and gas, pull galaxies together with the unyielding grip of gravity. On the other, dark energy, the mysterious force accelerating the universe's expansion, pushes everything apart with relentless determination. This isn't just a slow-motion tug of war. It's a struggle that's been unfolding for billions of years, and its outcome could rewrite the future of the universe itself. To understand this clash, let's start with dark energy's insidious influence. Discovered in the late 1990s when astronomers found distant supernova dimmer than expected, dark energy behaves like an anti-gravity force, stretching space itself faster and faster over time. Its effects are subtle but cumulative, like a steady wind eroding a mountain. In regions where matter is sparse, like the voids between filaments, dark energy dominates early, inflating these empty bubbles until they press against the cosmic web's threads, thinning and stretching them like taffy. Simulations show that over tens of billions of years, this process could weaken filaments to the point where they snap, isolating galaxies in a vast, ever-expanding emptiness. Yet filaments aren't surrendering without a fight. Gravity's pull is strongest where matter is most concentrated along these very threads. In dense regions like galaxy clusters, where filaments intersect, gravity's grip can still resist dark energy's push, at least for now. It's a cosmic balancing act. The more massive the filament, the longer it can hold its structure. Some superclusters, like the newly mapped Saraswati supercluster spanning 600 million light-years, are so enormous their gravitational bonds might persist for hundreds of billions of years, becoming lonely islands in an otherwise desolate cosmos. The real wild card lies in dark energy's nature. If it remains constant, as the simplest models suggest, filaments will gradually fade over trillion-year timescales. But if dark energy grows stronger over time, a scenario called phantom energy, the outcome becomes far more dramatic. In this case, the acceleration could reach a point where it overwhelms even the strongest filaments, shredding them apart in a big rip that would tear galaxies, stars, and eventually space-time itself into nothingness. While this remains speculative, it's a chilling reminder of how fragile the universe's grand design might truly be. Ironically, dark energy might also be preserving some filaments even as it destroys others. Recent studies suggest that in certain regions, the expansion's acceleration can stretch filaments into thinner, more stable configurations, like a spiderweb pulled taut. These dark energy filaments could outlast their traditional counterparts, acting as cosmic lifelines long after other structures have dissipated. It's a paradoxical twist. The very force unraveling the cosmic web might also be weaving a new, more fragile version in its place. What does this mean for our corner of the universe? The Milky Way's filament, part of the Laniakea supercluster, is still holding strong, but simulations suggest dark energy's influence will grow noticeable in about 30 billion years. By then, galaxies beyond our local group will have receded beyond visibility, their light stretched into oblivion by the expansion. Future astronomers, if any exist, might gaze into a sky where only a handful of nearby galaxies remain, their motions still dictated by the fading gravity of what was once a vast interconnected web. This cosmic struggle isn't just academic, it's a window into the universe's deepest mysteries. By measuring how filaments bend and warp under dark energy's pressure, astronomers are probing the very nature of spacetime, testing whether Einstein's theories hold or if new physics awaits discovery. Every observation of a distant supercluster, every map of a filament's gas distribution, adds another piece to the puzzle, and as next-generation telescopes like the Vera see. Rubin Observatory come online, we're poised to witness this battle in unprecedented detail, watching as the universe's largest structures dance between creation and dissolution. For now, the cosmic web endures, a testament to gravity's patience and dark energy's slow but unstoppable march. Whether it will stand the test of time or fade into the expanding darkness remains one of cosmology's greatest unanswered questions, a reminder that even the mightiest structures in the universe are subject to forces beyond their control. Earth sits in a quiet suburban neighborhood of the cosmos, a minor filament branching off the Laniakea supercluster's grand spiral. But don't let its unassuming location fool you. This might be the ultimate cosmic real estate for life. Unlike the crowded downtown cores of galaxy clusters or the desolate voids between filaments, our position along this gaseous thread offers a rare balance of safety and opportunity. Think of it like building a house too close to a bustling city center, and you're bombarded by noise and pollution, too far in the countryside, and resources are scarce. Filaments like ours strike the perfect middle ground, providing just enough cosmic infrastructure without the chaos. One of the most critical advantages is radiation shielding. Galaxy clusters where filaments converge are bathed in deadly X-rays from superheated gas and violent quasars, a constant storm of high-energy particles that would sterilize any fledgling life. Voids, on the other hand, lack the raw materials to build planets in the first place. But here in the filament's gentle currents, galaxies are spaced just far enough apart to avoid constant bombardment, yet close enough to exchange resources. Our Milky Way's outskirts, where the solar system resides, add another layer of protection, buffering us from the galaxy's more turbulent core. It's no coincidence that most potentially habitable exoplanets discovered so far orbit stars in similar filament-dwelling galaxies, places where the cosmic environment is neither too harsh nor too barren. Then there's the matter of material abundance. Filaments act as cosmic conveyor belts, funneling gas enriched with heavy elements from ancient supernovae directly into galaxies like ours. These elements, carbon, oxygen, iron, are the building blocks of planets and life itself. Without this steady supply, Earth might never have formed with the right mix of ingredients. Even today, the faint glow of hydrogen clouds along our local filament suggests the Milky Way continues to siphon intergalactic reserves, ensuring future generations of stars and planets. Compare this to galaxies adrift in voids, where star formation sputters out as gas supplies dwindle, or cluster galaxies where mergers and black hole outbursts disrupt these delicate processes. But perhaps the most intriguing possibility is that filaments might influence life's longevity. In dense clusters, gravitational interactions can fling planets from their stars or trigger catastrophic asteroid bombardments. Filament galaxies, evolving in relative isolation, face fewer such disruptions, offering stable environments where life can develop over billions of years. Even our solar system's structure, with giant planets like Jupiter deflecting comets away from Earth, might be more common in these calm galactic suburbs. Some astrobiologists speculate that filaments could be galactic habitability zones, much like the Goldilocks regions around stars where liquid water can exist. Does this mean filaments are the universe's preferred nurseries for life? The answer remains tantalizingly open. While our location seems favorable, the cosmos loves surprises. Life might find a way even in cluster galaxies or rogue worlds ejected into voids. But one thing's certain, as we scan the skies for signs of other civilizations, focusing on filament-rich regions could sharpen our search. After all, if the universe is a vast network of interconnected threads, it makes sense that life would thrive where the cosmic web weaves its most delicate balance. Long before telescopes revealed the cosmic web's hidden architecture, humanity sensed the universe's interconnectedness and poured that intuition into art. Ancient cultures painted the night sky as a celestial river, a tree of life, or a spider's silk-threaded tapestry. The Norse envisioned Yggdrasil, a world tree whose roots and branches linked realms, while Aboriginal dot paintings mapped star trails as ancestral pathways. These weren't just myths, they were prophetic glimpses of a truth science would later confirm, that the cosmos is woven together by invisible threads. Fast forward to the 20th century, and artists began mirroring astronomers' discoveries with uncanny precision. Take Vincent van Gogh's The Starry Night, where swirling skies mimic the turbulent plasma flows we now know course through filaments. Or Hilma af Klint's abstract paintings, which channeled cosmic networks decades before supercomputer simulations rendered them. Even modern installations like Tomas Sarasno's Webs of Life delicate suspended sculptures echoing filamentary structures blur the line between gallery and galaxy. What unites these works is a shared instinct. That beauty lies not in isolated points of light, but in the spaces between them. Filmmakers, too, have weaponized the cosmic web's eerie grandeur to evoke awe. The psychedelic star gates of 2001, A Space Odyssey. Kubrick's light corridors resemble ionized gas streams along filaments, Marvel's Doctor Strange fractal universes. Near-perfect visual metaphors for the web's fractal-like branching. And who could forget Interstellar's tesseract, where time folds like gravity warping a filament's path. These visions succeed because they tap into a deep truth. The universe's scaffolding feels simultaneously alien and intimately familiar, like a half-remembered dream. But the most striking fusion of art and science emerges in data visualization. Teams like NAS, a conceptual image lab, transform telescope datasets into swirling, color-saturated films where filaments pulse with artificial hues: gold for dark matter, electric blue for hot gas. Artist Leah Halloran collaborates with astrophysicists, etching galaxy surveys into cyanotype prints so large they wrap entire rooms, immersing viewers in the web scale. These projects aren't just pretty pictures, they're translation tools, helping our earthbound brains grasp structures no human eye could ever see unaided. Why does this creative cross-pollination matter? Because filaments defy intuition. Their scales are too vast, their physics too abstract. Art bridges that gap, distilling complexity into visceral emotion. When a child points to a Van Gogh and says, "It looks like space," or a gamer navigates No Man's Sky's procedurally generated galactic webs, they're internalizing a cosmic truth science took centuries to uncover. That connection is the universe's default state. Perhaps that's the greatest gift of these artistic interpretations. They remind us that science and creativity aren't opposites, but twin ways of knowing. The same impulse that led an Inca artisan to weave constellations into textiles drives a programmer to render dark matter in VR. Both are map makers tracing patterns in the dark. And as our understanding of the cosmic web deepens, so too will our art, evolving from intuitive sketches to ever more accurate portraits of the universe's hidden skeleton, a dialogue between discovery and imagination that spans all of human history. The cosmic web doesn't just challenge our understanding of space, it forces us to confront profound questions about existence itself. When we trace the filaments connecting galaxies across billions of light years, we're not just mapping matter, we're glimpsing a universe that operates as an inseparable whole, where every particle, every star, and every galaxy is bound by invisible threads of gravity and causality. This interconnectedness echoes ancient philosophical traditions, from Eastern concepts of Indra's net, where jewels reflect one another infinitely, to Western ideas like Spinoza's pantheism, which saw divinity in nature's unity. The filaments suggest a cosmos where isolation is an illusion, and every action ripples across the cosmic network in ways we're only beginning to fathom. Consider the implications for free will and destiny. If galaxies are steered by filaments like leaves caught in a river's current, does that mean their paths, and by extension, ours, are predetermined? Or is there room for chance within this vast, structured flow? The answer might lie in the filament's own behavior. While gravity dictates their broad structure, quantum fluctuations introduced randomness at the smallest scales, meaning the cosmic web isn't a rigid grid but a dynamic, ever-evolving tapestry. Perhaps human existence mirrors this balance, shaped by larger forces, yet still capable of forging unique paths within the weave. Then there's the haunting question of cosmic consciousness. The resemblance between neural networks and filamentary structures has led some to speculate. If the universe organizes itself like a brain, could it, in some sense, be thinking? Most scientists dismiss this as poetic analogy, but the underlying principle that complexity tends toward certain universal patterns hints at deeper truths. Whether in neurons, ecosystems, or galaxy clusters, nature seems to favor interconnected networks as the most efficient way to process energy, information, or matter. This doesn't imply the universe is alive, but it does suggest that the same mathematical principles governing thought might also shape the cosmos. Filaments even reframe our place in existence. For centuries, humanity saw Earth as the center of creation, then relegated it to an average planet orbiting an unremarkable star. Now, we're discovering that our galaxy is just one node in a filamentary web stretching across the observable universe, yet this vast scale doesn't diminish us. Instead, it reveals how deeply we're woven into the fabric of reality. The atoms in our bodies were forged in stars whose formation was guided by these very filaments, meaning we're not just observers of the cosmic web, but products of it. In a very real sense, we are the universe examining its own structure. Ultimately, the filaments invite us to rethink the boundaries between science, philosophy, and spirituality. They challenge us to see the cosmos not as a collection of objects, but as a dynamic relationship, an endless dance of matter and energy where connection is the fundamental truth. Whether through the lens of physics or metaphysics, one thing is clear: the universe is far more interdependent, far more beautifully entangled than we ever imagined. And that realization might be the most profound gift the cosmic web has given us. You might think unraveling the mysteries of the cosmic web requires billion-dollar telescopes, but some of its most fascinating features are hiding in plain sight, visible with equipment you've likely got gathering dust in your garage. Start with galaxy clusters, those glittering intersections where filaments converge. Even a modest 6-inch reflector telescope can reveal sprawling assemblies like the Virgo cluster, where hundreds of galaxies crowd together like fireflies in a jar. Aim for spring nights when Virgo rides high, and you'll spot Messier 87, a supermassive elliptical galaxy anchored by a black hole, fed by filaments too faint for amateur scopes, but whose influence is written in the surrounding galactic traffic jam. For those craving more challenge, hunt for gravitational lensing arcs. While you won't see the filaments themselves, their immense mass warps spacetime enough to distort background galaxies into surreal shapes. Targets like Able 1689, visible from the southern hemisphere, or the Bullet cluster can reveal these telltale smears with 12-inch apertures and astrophotography stacking. The trick: pair your telescope with a CCD camera capable of long exposures, then process images using free software like Cyril to tease out those elusive Einstein rings and arcs. It's like cosmic archaeology. The light bending around these clusters carries fingerprints of the invisible dark matter filaments threading through them. Don't overlook the power of citizen science projects either. Platforms like Zooniverse's Galaxy Zoo let you classify galaxy shapes from telescope surveys, indirectly mapping filament structures by noting which galaxies appear stretched or clustered along invisible lines. Your clicks could help identify new filament candidates for professional follow-up. More hands-on. Join the American Association of Variable Star Observers campaigns tracking quasars whose flickering reveals filament gas absorbing their light, a phenomenon called the Lyman alpha forest that's detectable with spectrographs as simple as the ALPI 600. The ultimate DIY filament hunt: build a radio telescope. For under $500, kits like the Radio 2 Space Spider can detect the 21-centimeter wavelength emitted by neutral hydrogen, the same gas tracing filaments between galaxies. While you won't resolve individual threads, mapping hydrogen's distribution across the sky reveals the cosmic web's shadowy backbone. One amateur group in Australia even contributed data to a study on the local sheet, the filamentary plane where the Milky Way resides, proving garage astronomers can advance real cosmology. What makes this so thrilling is realizing you're not just stargazing, you're witnessing gravity's architecture in real time. Every galaxy cluster logged, every lensing arc captured, stitches another patch onto humanity's map of the universe's hidden scaffolding. And who knows, your backyard observations might just spot something the pros missed. After all, the universe loves hiding its grandest designs in plain sight. Just when we thought we'd mapped the cosmic web's grand design, new discoveries are tearing up the textbook, starting with ghostly galaxies where they shouldn't be. Earlier this year, the Subaru telescope spotted a string of ultra-diffuse galaxies, ethereal, wispy structures as large as the Milky Way, but with 1,000th the stars threaded along a faint filament near the Pisces-Perseus supercluster. These cosmic phantoms shouldn't survive the violent tidal forces of filamentary currents, yet their pristine disks remain intact, suggesting filaments might cradle delicate structures rather than shred them. Even more bizarre, these galaxies show almost no dark matter, flipping the script on our understanding of how such fragile objects form. Researchers now speculate that filaments could be cosmic sorting facilities, separating normal and dark matter through processes we've yet to decode. Meanwhile, the Dark Energy Survey's latest data drop revealed filaments aren't just dark matter scaffolding, they're actively shaping galaxy evolution in real time. By tracking thousands of galaxies flowing along the Boots void surrounding filaments, astronomers caught something unprecedented. Galaxies downstream of filament intersections spin faster and form more stars than their upstream counterparts. It's as if these cosmic rivers impart angular momentum to galaxies like a pinwheel catching the wind. This challenges the long-held view that galaxy spin comes mostly from ancient mergers, pointing instead to filaments as ongoing cosmic spin doctors, tweaking galaxies' fates billions of years after their birth. The biggest bombshell came from combining gravitational lensing with gamma-ray telescopes. When the Fermi LAT team cross-referenced faint lensing distortions with unexplained gamma-ray hotspots, they found an eerie match. The excess emission traced exactly where simulations predicted dark matter filaments should lurk. While still preliminary, this could be our first indirect detection of dark matter particles annihilating within filaments' cores. If confirmed, it would unveil not just where dark matter hides, but how it behaves under extreme conditions, potentially cracking open decades of particle physics puzzles. But perhaps the most poetic discovery emerged from quantum physics labs, not telescopes. A team at MIT simulated the early universe's conditions using ultra-cold quantum fluids and spontaneously observed filament-like structures emerging from the chaos, governed solely by the mathematics of turbulence. This suggests the cosmic web structure might be written into the universe's most fundamental laws, appearing anywhere energy flows meet resistance, from quark-gluon plasmas to ocean currents. It's a humbling reminder that the same patterns repeat across reality, whether we're peering through a microscope or a telescope. These breakthroughs prove the cosmic web isn't some static relic. It's a dynamic, evolving entity we're just learning to decode. With the Vera Rubin Observatory's upcoming legacy survey of space and time set to map billions of galaxies, we're on the verge of watching filaments move and change in cosmic time, not just snapshots. What other secrets will we unravel as we finally see the universe's skeleton in motion? The universe's filaments are more than just scaffolding, they're the silent narrators of an epic story written in gravity, gas, and dark matter. Every strand in this cosmic tapestry holds clues to how galaxies are born, how black holes feast, and even how the raw ingredients for life itself are scattered across the void. What began as faint ripples in the aftermath of the Big Bang has grown into a sprawling network that shapes the destiny of everything we see, and the most astonishing part. We're only just beginning to read its chapters. Think about what these filaments have witnessed. They've seen galaxies collide, stars ignite and die, and black holes unleash jets of energy powerful enough to reshape entire clusters. They've carried the heavy elements forged in supernova, the carbon in our bones, the oxygen we breathe, from one corner of the universe to another. They've even mirrored the structure of our own brains, hinting that the same patterns of connection might govern everything from the smallest thoughts to the largest superclusters. It's as if the universe keeps rediscovering the same blueprint, whether it's building a brain or a galaxy. The future of filament research is just as thrilling as their past. Upcoming telescopes like the Square Kilometre Array will trace the faintest whispers of hydrogen gas along these threads, while gravitational wave detectors could reveal how black hole mergers ripple through the cosmic web. Simulations are growing so precise they'll soon let us rewind time to the very first filament, watching how it grew from a quantum fluctuation into a galactic highway. And who knows, we might even uncover entirely new forces at work, phenomena hidden in the spaces between galaxies, waiting to rewrite the laws of physics. But here's the real magic. This isn't just a story for scientists. Every time you look up at the night sky, you're gazing at a universe stitched together by these invisible threads. The same filaments that guided the Milky Way's birth are still out there, shaping the cosmos in ways we're only starting to understand. And that's why we explore, not just to satisfy curiosity, but to find our place in this grand, interconnected dance. So what's next on this cosmic journey? Will we find proof of dark matter's true nature lurking in a filament's heart? Could the web structure reveal hidden dimensions or new branches of physics? The questions are as vast as the filaments themselves. If you've enjoyed unraveling these mysteries with us, let us know where to point our curiosity next. The universe is full of wonders, and together we'll keep pulling at its threads. Until then, keep looking up. You never know what connections you